conservation of energy. Person, do not do this experiment at home, right? Leaping from a 10-story building from the very top, leaps down into a bucket of water. Do you promise that you're not going to do this experiment? Do you promise? Awesome. Extra credit to you for promising. Okay, good. We have at least one student who's going to survive this physics course. I'm so glad. Okay. So presumably this person hopefully has a bungee cord or something, but to the first approximation, they're ignoring the bungee cord, right? So person is jumping off the top. At the very top, they have a potential energy of 10,000 units of energy. Kinetic energy is 0 because the person is stationary. Person starts accelerating down. A quarter of the way down, now the person's kinetic energy is 2,500 energy units. Potential energy is 75. Notice 7,500. Notice that the sum of it is still 10,000. At the halfway point, potential energy is 5,000. Kinetic energy is 5,000. The total is the same as up there, 10,000. So all that happened is potential energy, one form of energy got converted into another form of energy. There was no energy that was created or destroyed by this process. Go further, potential energy 2,500, kinetic energy 7,500. At the very bottom, kinetic energy in this case is 10,000. So the person is traveling the fastest at the bottom here. And the potential energy is now 0 after they reach the ground. So all that's happening in this illustration is potential energy is converted into kinetic energy. Of course, if they do not have a bungee cord or something of that sort, they will go splat into this and end up at the very least in the hospital, right? If they had a bungee cord, what happens is as they drop, this kinetic energy gets converted into elastic stretching energy of the bungee cord. So when they reach the bottom here, you want the kinetic energy to be 0. And it's all translated into a different kind of potential energy, that of the bungee cord, which then pulls them up, right? Then they oscillate back and forth. Okay, so this illustration basically talks about potential energy of that anvil up there. Break the string, anvil drops. The anvil then gets converted into the anvil is accelerating downwards, so it's traveling with a certain kinetic energy, which then hits this piston and compresses this and comes to a stop. So potential energy got converted into kinetic energy, motion of the anvil, which then got converted into heating up the gases inside this piston or the cylinder. So it becomes thermal energy. So you can see one kind of energy translated into another, then into another. Another example here, you have a cannon shooting a cannonball that travels up here to the top and then travels down here and ends up here. What happens is the gunpowder stores energy in the form of chemical energy. Set fire to it, spark, whatever. The chemical energy gets converted into kinetic energy of the cannonball. As it travels up, the kinetic energy gets converted into potential gravitational energy up here. Then the potential gravitational energy gets converted into kinetic energy again until it comes and hits here. The kinetic energy, then the cannonball hits or whatever and breaks things, right? And so that energy gets converted into heat, which is basically kinetic energy of the molecules. So again, an illustration of energy being converted from one form to another and then another form. Okay, introducing the concept of a machine. A machine, and just a reminder, all of these slides are up there on the website, right? So you're welcome to download them as in handout form and write notes on them and so forth. A machine is any device that changes a force. Apply a force, it changes the direction of the force, or apply a force and it gives you a bigger force or a smaller force. That's a machine. Example of a machine is a lever, like a seesaw, right? So here's a seesaw. There's the fulcrum. If you apply a small force at one end of this through a large distance, small force through a large distance, if, for instance, this lever, or if you think of a seesaw and you have the seesaw pulled away so that the fulcrum is not centered, what will happen is now this force multiplied by distance, small force multiplied by big distance, as here, will be equal to, on the other side of this, a large force through a small distance. So the machine basically takes the small force that you applied over a longer distance. Remember that work done is force multiplied by distance. So you're putting work into this machine, you're getting the same amount of work out. However, the distance traveled is very small, so the force is large. This is the concept that is applied in this case, where you've got a little girl who's lifting up this whole car, right? So she's got don't do this experiment at home, but she's got this whatever, thingamajiggy, lever system that is hooked up to the car. She just moves this arm up and down through 25 centimeters, so just ballpark of about a foot, right? Like 30 centimeters is a foot. So she moves it up and down through a larger distance, and the way the lever is set up, what happens is the car travels up a small distance. So she is able to apply a smaller force. That work done, small force multiplied by large distance becomes equal to a larger force multiplied by a small distance, and that's how she's able to jack the car up. So little force applied by her over a large distance is equal to a large force applied on the car by the jack over a small distance. So the numbers here would be, she can apply 50 newtons over 25 centimeters, all of a sudden becomes 5,000 newtons over 0.25 centimeters. So each time she jacks us up, the car travels up a little higher and higher, right? That's how you could literally have a little kid jack up a car. Okay, introducing the concept then of efficiency. Efficiency is the percentage of work that you put into a machine that's converted into useful work output. So it's kind of like saying, if you were to put $10 worth of work into a machine, how much worth of useful work comes out at the end? So if you think of solar panels, for instance, right? Solar panels, not uncommon to have solar panels that have an efficiency of what? Does anybody know? 6 or 7%? 6 or 7? Okay. So let's say that we have a really efficient solar panel and it's giving us 7%. Which means if you put in $100 worth of sunlight onto the solar panel, $93 worth of sunlight is just completely wasted. Just $7 worth is coming out. So it's a really low efficient system. This is why there's a lot of room for you guys, like if you get into technology and come up with some amazing invention that increases the efficiency of solar panels by a factor of 10. So even like 70% solar panel would be totally amazing, right? And just as an experiment, I basically got solar panels on my house, and half of the area, I think it's the entire southern side of the roof and part of the western side is covered with solar panels to roughly equal my power bill. Now if you increase the efficiency by a factor of 10, what you could do is power your entire house with a solar panel that's probably about the size of maybe 2 of these tables in terms of area. Wouldn't that be amazing?
Part of the ratio is that it'll degrade the panels. So if you have more efficient panels, it'll degrade
It degrades faster. Okay. Yes. So that's a trade-off when you're actually extra credit for speaking up, when you're actually creating the solar cells and so on, right? So you could have higher efficiency, which could end up, as what you're saying, with lower reliability, right? It doesn't last as long. Good. In principle, not. That is by which I mean, I get a bill of normally my average power bill used to be about $125 a year, averaged out, and now my bill is 0, right? So, or maybe $20, something like that.
How many years do you have to use it before you?
That's why it's really not worth it. It's not worth it because of the cost, because they're very expensive. So if you went to the 14 kilowatt, there's a cutoff, like you can get like a 14% return on investment, they said, which is a rip-off because they tax you on the rebates. I just found it after the fact, right? Like my system was like probably like $28,000 and I got a $10,000 rebate, which I then got taxed on at the end. And by the time I do all of that, it's like a 3% bond. I'm getting a return. It'll take 33 years to pay it off, right? Maybe 5%, something like that. So I just went ahead and I did it just because I wanted to see, like I wanted to see the technology, right? And for no other particular.
33 years?
I'll probably be dead by then, but but somebody else may. I don't know. I think it's polysilicon, so it should be PV panels, is my guess, right?
It's a very efficient way to produce.
Yeah. So come up with a way of like totally at good cost, and you can probably become a multi-millionaire. More power to you, right? So efficiency is the percentage of work that you put into the machine is converted into useful work, right? So let's say useful work. Let's say that you're trying to study for a physics test, and useful work is like you're studying, like you're like really drowsy or whatever. You spend 3 hours studying, like half asleep, right? And you get 15 minutes worth of knowledge out of it. The efficiency would be the 15 minutes divided by the 3 hours multiplied by 100, right? As a percentage. So obviously the moral of the story is be properly rested and study when it's your best time. Like if you're a morning person in the morning, if you're a night person at night. Cool? So I'm going to go ahead and put this off.